Welcome to the fourth day of Summer General Physics. In this second video, we'll be continuing to look at projectile motion. Specifically, we'll be looking at a problem that involves the range equation. So here's the example problem. Could the bus have made it? Hopefully by now you've watched the speed video clip and seen the bus jumping the gap. Could the bus have actually made it in real life? So before we solve this problem, we're going to have to collect some information or write down some information regarding the motion of the bus. One thing that was stated was that the gap in the bridge was 50 feet. So that was a bit of the dialogue that was missing from this particular clip, but if you watch a larger clip containing this segment of the movie, they state that the gap is 50 feet that the bus needs to jump across. Also, if you look at the speedometer of the bus as it nears the gap, it's in the upper 60 mile per hour range. So assuming that the bus maybe lost a little bit of speed as it was going up the incline towards the gap, we could have a conservative estimate that the bus was launched at a velocity of about 65 miles per hour. So let's write that down. So I'm going to estimate that as the bus started flying through the air, its launch speed, or its initial velocity, was 65 miles per hour. Okay, so let's convert that, of course, to meters per second. So 1 mile per hour is approximately equal to 0.447 meters per second, which means that the initial velocity of the bus would have been around 29.1 meters per second. So I'm also going to assume that the bus started and stopped at the same height. So it had some initial velocity, and it took off, and it crossed this 50-foot gap, and then landed at the same height. Draw that a little better, but it landed at the same height that it took off at, and so there was, its delta y would have been 0. Its final height was the same as its initial height. The other thing I need to know, so that means I can use the range equation because I satisfy that special circumstance that the takeoff height and the landing height are the same. So the other thing I need to know to use the range equation in order to figure out the range would be the launch angle. And if you look at the movie, actually I paused the movie right before the bus gets to the incline and kind of took a protractor to it and tried to figure out the incline right before the takeoff. And it looked to me like the incline of the ramp was about 8 degrees. So we'll assume theta, the launch angle, is 8 degrees. Okay, so let's try putting that into the range equation. So our range, which is the same thing as the displacement in the x direction, is equal to the initial velocity squared, and I don't have to worry about breaking it into x or y components. The range equation uses the whole thing, times the sine of 2 times the launch angle divided by g. So putting in some numbers, the initial velocity we estimated was 29.1 meters per second. We have to square that times the sine. 2 times our 8 degrees would be 16 degrees. And then we divide all of that by 9.8 meters per second squared. So we get a range then, or a delta x, of 23.8 meters. So that would be the distance traveled in the horizontal direction by the bus. So if I'm going to compare this with the 50-foot gap, I should change the meters back to feet. So 1 meter is the same as 3.281 feet. So that gives me a range of 78.1 feet. So it looks like, according to our calculation anyway, that the bus could have made it. It could have made this, this jump or this leap across the gap. Now, the rearing up into the air, maybe that's not quite as possible, and the fact that its tires did not explode upon landing, maybe not also the most realistic, but in terms of assuming the bus is a projectile, then maybe it could have made it across the gap. So here's a question for you. Let's suppose that there is a projectile that's launched with an initial horizontal velocity of 2 meters per second and an initial vertical velocity of 2 meters per second. What's the speed of the ball at the top of the parabola that it travels along? So pause the video here, give that a bit of a think, and then continue once you have your answer. Okay, so if you've decided upon your answer, let's take a look at this question. So we have this projectile, and the projectile is going to be launched so that its initial horizontal velocity is 2 meters per second. Its initial vertical velocity is also 2 meters per second. And so the total initial velocity looks something like this. So this particle is going to continue on a parabolic path, and we want to know what is the speed of the ball here at the top of the parabola. Well, we can most easily think about this question if we break the motion up into components. We know that the horizontal velocity never changes. If it's 2 meters per second here, then it's 2 meters per second here, here, and at the top as well. So the vertical, or the horizontal component rather, of the motion is also 2 meters per second at the top of the parabola and continues on this side as well. As far as the vertical component, it's 2 meters per second here, but as the ball goes up, the vertical component of the velocity gets less and less, the ball slows in the vertical direction, and then at the peak, its vertical velocity is 0. And then the acceleration starts building vertical velocity in the downward direction on the second side of the parabola. So here, all of the motion is in the horizontal direction, and since the motion in the horizontal direction, the velocity in the horizontal direction never changes, then at the top of the peak, the ball will be going 2 meters per second. So that concludes video 2. In the next video, we'll be looking at circular motion and the kind of acceleration you get because an object is moving in a circle, which is called centripetal acceleration.